All right, welcome back, everybody. So today we're finally going to be learning how to solve, systems of differential equations, systems in first order technically, but so systems of first order differential equations, and we're going to be solving these with our beautiful exponential matrix, which we worked so hard to define, matrix exponential. So let's look at, we're going to basically step our way through all four styles of Cauchy problem and see which ones are actually, somewhat easy to solve in the way that we might want to, because we're going to find out pretty quick that we can solve some of them really easily with this matrix exponential, and some of them we just can't. So we'll see the total extent of our power of this matrix exponential right now. So we'll just start out with the simplest case, which you'll recall is this homogeneous autonomous Cauchy problem, where I'm reducing myself to finite dimensional spaces now, which I kind of mentioned in the previous lecture, where we're going to think of our vector space V as d-dimensional complex space, and every single L in the Cauchy problem is just going to be a matrix. So we're looking at the time evolution of some function. In this case now I'm calling it y. It's vector valued. It equals a matrix on that function. And then this is also an initial value problem, so I have y defined as some initial vector. So it turns out it's really easy to find the solution as long as we're in finite dimensional spaces. Here's my theorem. It says that the solution to this initial value problem is given by the matrix exponential. I've shifted time to my initial value, right? If the initial time is t0, I have to shift time to t0, and then I take the matrix exponential and I act that on my initial vector. And in particular, e to the tm has to be defined as in our theorem, where we know how to define matrix functions. So this is actually really easy to do theoretically, right? We have a very clear solution of this particular equation. But let's actually look at an example of this and see maybe if it's a little bit trickier. So let's evaluate this system, linear system of ODEs from the previous section. This was our nice example of a homogeneous autonomous Cauchy problem, but as a system of linear first order differential equations, it's not so clear how we might write this or solve this using our theorem that we had above with the matrix exponential. And so that's why it's important that we recognize kind of this idea of rephrasing systems of ODEs as vector valued ODEs, right? What we're doing is we're reconsidering the system as vector valued ODEs. Now I just have a vector prime on the left, a vector on the right, and some matrix between the two of them. Because in this sense, this is a Cauchy problem. It's maybe a little bit not right to talk about the system as a Cauchy problem, but once we convert the system into this kind of vector valued ODE, then it is a Cauchy problem, and hence we have a solution. So our theorem tells us how to find the solution of that. We just need to compute the matrix exponential. There's our matrix M. To compute the matrix exponential, we're going to form our Jordan decomposition. And thankfully, for a 2x2 matrix, in this case, we have two independent eigenvectors. And these are 5 plus or minus I root 3 over 2. You can compute that with your characteristic equation. And we recover eigenvectors where they just actually have a really bad number in the first component and just 1 in the second component. But the plus or minus exactly corresponds to the plus or minus from lambda. From above, it's not too hard to compute the eigenvectors either. And so we have our matrix which diagonalizes M. Therefore, we can write M as X, this X matrix times the diagonal matrix, where the diagonal entries are the eigenvalues. And make sure, this was something that I think is often forgot. We need to make sure that these pair correctly. So this has to be the eigenvector, which corresponds to that eigenvalue. This needs to be the eigenvector, which corresponds to that eigenvalue. So we want to make sure you pair the vectors in X with the correct eigenvalues when you take the diagonal. But then we have our diagonal, and it's really easy to compute the exponential matrix then, because we're just computing the exponential matrix of the diagonal, which is just the exponential on each diagonal term. And I think my 2 is in the wrong spot there. I think everybody can see that. So this 2 should be, the 2 and the D should be swapped on those two. But aside from that, that's correct. So we compute the matrix exponential. Hopefully everybody sees why I didn't have to shift time here. This is t minus t naught. But if I scroll up to my problem, we recognize that t naught is 0. So it really helps when t naught is 0. That means we just compute the standard matrix exponential, which is given. And then we actually compute it with x and x inverse, and we get something that's a little bit ugly. It's not the prettiest thing in the world. right? I don't think anybody agrees that that's a pretty solution, at least the exponential matrix, but it exists. It's well written. You can write the whole thing on one line of page. And then if we act that matrix, this is our matrix exponential. If we act the matrix exponential on the initial condition, which let's recall the initial condition was the vector 2, -1. If we act the matrix exponential on the initial condition, we recover a vector. This is now x of t is a vector which depends on time. And that vector is x1 of t, x2 of t. So the entries, we can pair them 1 to 1, where x1, x2 solve the system of ODEs from the beginning. So that's how we actually compute solutions to these sort of Cauchy problems or systems of ODEs, and I've provided a plot on there. Not that it's really providing anything super useful for us, but you can at least see the trajectories of x1 and x2, and it's nice to verify, okay, x1 should start at 2, x2 should start at -1, and if we look at the y-axis, that's true. So x1 starts at 2 and x2 starts at -1, and they just kind of flow in their trajectory over time, right? Okay, so then we're going to kind of step up in complexity, and we're going to gain ourselves an inhomogeneity, or rather, this Cauchy problem is going to have some additive function on it. And so there's our generic example. Now we've reduced ourselves to finite dimensions. That's just why I reintroduced the definition. But there's our example of a generic one of those. And to solve one of these, here's our next theorem for today. Today is just chock full of theorems, by the way, so just trying to pay attention every time a theorem shows up. It says this theorem specifically solves this sort of Cauchy problem, and then kind of just lock those in the back of your head. You can always refer to the book later as you're completing problems. But here's our second theorem. It basically says if we have an inhomogeneous Cauchy problem, but it is autonomous still, we can solve it with something called Duhamel's principle. Now, Duhamel's principle won't normally be phrased in this form, but this is definitely the way that you can think about it if you want to. This is my favorite way of thinking about Duhamel's principle. Most of the time, it'll be mentioned in a PDE's course instead, because it's a little bit more broadly defined there. But basically, what Duhamel's principle says is that we have this is our solution from the previous section when we didn't have a forcing term, right? Now we have an additive function, which we sometimes call a forcing. So we have an additive function here, but our solution starts out looking the same way as it did before. This is the same solution we had in our previous theorem. However, we have to account for the additive function by computing an integral of the matrix exponential shifted by s. Now, what is s? S is just some parameter which we're integrating over, but we integrate from our initial time to where we're standing now. So really the way that we would see how this is proven is you just take a derivative. You take a derivative of that integral term, and you're going to find out with the product rule that you recover the matrix on that same integral term, and then you add the forcing term. So that's basically where we're going to recover the forcing term from here, is because we have a derivative of something. When you take a derivative of this integral, you're going to recover the forcing term. And that's why Duhamel's principle works in this case. But this is definitely like a considerable amount of extra work that we have to pay the price for just having one forcing term. So a full integral along with another matrix exponential is a lot of work that we have to pay the price for a forcing term. But let's see that in action. So as in the previous chapter, or the previous section, I suppose, we have our inhomogeneous autonomous Cauchy problem, but it doesn't necessarily look like it right now. But there's our additive function, hence inhomogeneous. So we can see the additive function in our system of differential equations, where now if I scroll down a little bit, I should have a plus f of t here, right? So that's a bit of a typo. So this is really plus t cosine t. So that's actually my Cauchy problem for this system of ODEs, because I have this t cosine t that shows up. And so I have the additive functions there, and I do correct it later, of course. Yeah, I got f here. So I do correct it later, and we can recall what our matrix exponential is based off of the last section because the matrix has not changed. The matrix M is the same as in the last section, but now I just have to compute my extra Duhamel's principal term, right? So the matrix exponential is the same as before, but if I look at my solution then, my solution has the same solution we had before, but I have this special Duhamel's principal term, and you'll notice what I've done to utilize Duhamel's is f of s goes into the integral, and the integral is computed from t naught up to t. And then I have this s sitting around my integral that I'm integrating against. So this is Duhamel's principle in action, and we just actually have to compute this. And it's a little tricky because we have to compute the exponential matrix, which itself was already ugly, evaluate it at t minus s, and then act that entire matrix on the vector s cosine s. So I'm putting s cosine s against this matrix, and I'm going to get something even uglier. There it is. So it's this one right here, right? So this is me taking the entire exponential matrix, evaluating it at t minus s, and acting it upon my forcing function. And I just used a computer, and I think you should too. I'm never going to ask you to do these crazy ones by hand. Do this on a computer. But once I do that on a computer, I recover the following. And, it's a little bit ugly, but it fits on a page. And you'd be surprised how often we have some mathematical solutions which do not fit on pages. So that's this. Recall, this is just the Duhamel's addition to the solution, where my initial value addition, I'll call this the IV initial value solution. So I have an initial value solution and the Duhamel's addition. I'm going to add them together to get the true solution here. So once I add them together, there you go. It's split onto 2 pages because it's relatively large. But there you go. You add them together and you actually get a solution. And I can plot these again. And you'll notice that once again, we do start with x1 initializes at 2 and x2 initializes at -1. And then they evolve independently from there. I mean, not independently, but they evolve on the plot from there over time. And if we just want to compare really quick, what has the forcing done to my solution? Well, you'll notice that this one, x2, in the old solution, x2 jumps up a lot faster and x1 kind of peaks downwards, versus my forcing has kind of dampened both of those a little bit. And we could compute how this is a damping force, but you'll notice that neither of them are really moving quite as fast as they were before. So this isn't jumping up as high, that's not peaking as high. And so our forcing has changed it a little bit, obviously not very much, because how does the forcing behave at least near our initial condition, near 0? Well, the forcing in x is 0 near the initial condition. The forcing in x2 is 1 near the initial condition, but cosine eventually oscillates back down to 0. And so the forcing is not super intense in this problem, which is why our solution looks somewhat similar, but definitely distinct from what we had before. So we're moving up in the hierarchy of difficult Cauchy problems, and actually we have basically, I'm going to draw a line here. We've now exhausted the easy solutions. And I know a lot of you are looking at the solutions we came up with above and are wondering why that's easy. It's easy because you can actually do it, right? The computer, you plug it into your computer, we clearly got something that works. We're going to see on the next one that's not really easy anymore. So let's recall what it means for us to be homogeneous but non-autonomous. Non-autonomous means our matrix depends on time, but homogeneous means we do not have forcing. So there's no additive function on here, but our matrix depends on time. So there's our Cauchy problem we're working with, and just take what I present to you now with a huge grain of salt. I don't need you to focus on any of it. I don't need you to understand any of it. I want to show you that it's possible and leave it at that. Okay, so to get to our theorem to solve this problem, I need to define a few things that are going to seem like way out of left field, because I'm basically introducing like second-year graduate math to you in like 3 paragraphs. So just take it for what it is. Use this section as a reference manual if you ever happen to get to that point where you want to, but otherwise just watch it and be happy. So we have something called the commutator of matrices, and this isn't necessarily too crazy, but we do have to define it. It just asks the question, how commutative are the matrices M and N? I'm going to calculate M times N minus N times M. If they're commutative, this will be 0. If they're not commutative, it'll be some other matrix, right? That's a matrix, that's a matrix. If I subtract 2 matrices, I gain another matrix. And so this is some matrix which kind of represents a matrix whose, in many cases, norm represents the degree of non-commutativity, sure, of m and n. So in some sense, we can like measure how commutable m and n are with this thing called the commutator. And it's just got a very nice notation of the brackets. And I do want to mention that there's a remark here where a lot of you, maybe not a lot of you, but a few of you have maybe heard of this thing called the Lie bracket, and you maybe were introduced to the Lie bracket exactly in this way. It's not the same as a commutator. The commutator is a special case of the Lie bracket. You can have Lie brackets that aren't necessarily commutators, but every commutator will be an example of a Lie bracket. And then we gain this thing, which is a linear map. It's a linear map on the space of matrices. So what the linear map is you fix a matrix M and you just compute the commutator against whatever matrix this runs into, and we call this the adjoint representation. Once again, don't put too much work into it. Just think about it as a map from matrices to matrices. And now we get to the point where we actually can develop a theorem which will solve our non-autonomous Cauchy problem. So I'm going to say that the solution to equation 6.3, which was our non-autonomous Cauchy problem, here's our non-autonomous Cauchy problem. The solution to that by this theorem is given by e to this script m, t comma t0 acted on the initial condition. Okay, so this looks very similar, right? How bad can it be? This looks very similar. It's very similar to e to the tm, right? Or even e to the t minus t naught m. So how bad can this actually be to solve the non-autonomous system? Well, why would I have gone to where I went? What is this calligraphic m t of t naught? Well, it's an infinite series. Okay, still not that bad, right? It's an infinite series of m sub n. Okay, so now I've indexed these things. Interesting. And how do I calculate these m sub n's? Well, I calculate the first one. That's just m of t. So this is in fact the linear operator of the Cauchy problem. Okay, so the first one is the linear operator of the Cauchy problem. But the rest of them, what do the rest of them look like? The rest of them, from that point onwards, these are defined recursively based on the previous ones as a sum from 1 to all the way up to n of all combinations of ki's, which are non-zero, which themselves sum to n minus 1. And then I integrate, and I take a bunch of compositions of this adjoint representation, which I was talking about, of a lot of the previous mk's, and I take all those compositions and I act them on the first one, and then I have to integrate from 0 to t. Oh yeah, that's just to produce a single one of these mn's. Then I take the infinite sum of all of those. So, yeah, we're not going to be solving any of these non-autonomous Cauchy problems anytime soon. I've never used this in to truly calculate the solution. You can use this to provide some nice properties of your solution, right? You can like argue that the MNs maybe have some very nice formula that you can start to see a pattern in them, and then argue that your solution is well behaved because of that. But for all intents and purposes, this is as bad as trying to calculate the next prime by just taking every number and dividing it by all of the previous primes, and then you fail repeatedly until you get to the next prime. So this is pretty bad, but it technically gives us a solution, right? Because then there's our solution once we calculate. Well, yeah, and even at the end of the day, this just gives us a matrix, right? So the infinite sum of these is itself a matrix, and then we calculate the matrix exponential of that on our initial condition to get the solution. So we are not going to use this theorem ever, but it's nice to see that it exists, since theoretically we could do something with it. We get away way easier if the commutator of the time-dependent m with another time-evaluated m, right? So if I can evaluate m at two different times and the commutator is always 0, I'll write this down a little bit more explicitly. If mt1 commutes, because remember, matrix multiplication is not commutative, commutes with mt2 for all time t1, t2, then we can actually get away with something way easier that's a pretty easy matrix exponential to calculate. It's just the antiderivative of m with respect to s, right? So we're going to take the antiderivative of that matrix and then take the matrix exponential there, and everything falls through. So these are the cases that we might be able to talk about, and that's why it's left as a corollary. And in fact, there's an even slightly easier corollary if in fact the matrix, which depends on time, is just some gamma, or whatever you want to call that, some function of time that you can factor out of the matrix. Maybe I'll make that clear here. If you can factor all functions of time out of the matrix, then we can also get a really easy solution. Okay, so then our solution, all we have to do is integrate that function which we factored out of our matrix, multiply that by the matrix, and then take the matrix exponential of that. So there are these two corollaries of our Magnus expansion are actually really nice, right? These are really elegant examples where we can still calculate these pretty easily. The true Magnus expansion, where this doesn't hold, is really not gonna be helpful for us. But these other two corollaries are nice. Okay, so in this particular problem, this is a modification of our homogeneous autonomous system, and I've modified it by putting a t on every term. So now it's non-autonomous. Say non-autonomous, since the linear terms depend on time. So I've modified it by multiplying all of them by t, but the nice thing is, because I multiply all of them by t, basically, rather than representing my matrix as 4t, 3t, negative t, and t, I represent my matrix as 4, 3, negative 1, and 1, and I factor out a t. Factor out t, then the matrix which depended on time is now equal to this gamma, which depends on time, times a matrix which doesn't depend on time, in this case, for gamma equal to t. Right, so thankfully in this case we can apply the above corollary, which made my life a lot easier for these non-autonomous systems. And in doing so, right, I'm just going to integrate gamma in my matrix exponential to get t squared over 2. And there's my t squared over 2. And compute that matrix exponential with a t squared over 2, right? That's why we have t squared in every term here, on the initial vector 2, 1, and I recover my solution just as before. Now we can see what's happened. We still initialize at 2 and negative 1, but it's almost like we zoomed in. It turns out these situations are a change of variables. The time from our first situation changed to gamma t. So it's like this t-axis has been stretched under t squared, the mapping t squared integral. So it's like that has been mapped to t squared from our previous solution in some ways. T squared over 2, I guess. Anyway, this is a result of the corollary, which we can actually use, even though the theorem we cannot use. Finally, we're one more sort of Cauchy problem here. This is just Duhamel's principle with non-autonomous systems, right? So suppose we're non-autonomous, that means the matrix depends on time. Suppose we're non-homogeneous or inhomogeneous, which means that we have a forcing function. Then I can find the solution using Duhamel's principle. And this is the exact same Duhamel's principle we had before, but now I'm dealing with my beautiful curly m that nobody ever wants to calculate, because it's going to absolutely destroy you if you try. Okay, so let's just see the example in the corollary cases, right? So my same corollary cases apply. If I have commuting matrices, I just apply Duhamel's to those situations. Or if I can factor out gamma from my matrices, I apply Duhamel's in those situations, and I still get my solution. So once again, these corollaries are going to be super useful for us. Right? If we have a non-autonomous, inhomogeneous Cauchy problem, then I ideally can factor out gamma, or for some other reason the matrix commutes with itself at all times. And then I can apply one of these corollaries, because I do not want to calculate the script m. Okay, so let's look at an example. All I'm going to do is take our previous example that we just solved for, but I've added a forcing function plus t plus cosine t. And so the forcing function is there with t and cosine t, and I'm able to factor out gamma from my matrix, so now my matrix M sub t depends on gamma, but it depends on gamma out front. So all I have to do is compute the matrix exponential solution of the previous one. This is like e to the, I'll write that more explicitly. This is e to the integral s to t of gamma of u du for this specific problem times m. And there it is. And then de Mols will give us the solution just by evaluating that matrix exponential on the initial condition and then my beautiful integral against the forcing function. And I did not place this on in the book because it takes up not quite a page, but it takes up a lot. So, we're getting to the point where like there's a reason why we do a lot of these things on computers, because they give us solutions. I can actually go ahead and plot the solution, but there's no way I would ever want to do this by hand or write it down, right? So that's something really nice about this class, is we're learning how to actually solve some really difficult problems, but on computers. And so there's the solution. You can see it's kind of a modified version of what we had before. Once again, thankfully, x1 still starts at 2, x2 still starts at -1. Anyway, that's all I have. I know it was a lot. This is probably the hardest section dealing with like simply solving ODEs in this entire class, because once we solve these, everything else becomes a special case of these. But we are going to be forced to start doing them by hand, whereas in this section we're doing them on a computer. So the computer kind of helps us here, even though the ODEs can be really ugly. Anyway, I'll see you in class. Bye.